wind-blown sand from the Gobi Desert. Such large temperature variations have a destructive effect on the exposed rocky surfaces. The repeated fluctuations put a strain on exposed rock and the flanks of mountains crack and shatter. Fragmented strata slide down into the valleys where they continue to break into pieces due to the relentless sun by day and chill by night. Successive strata are exposed to further weathering. The relief of the internal pressure that has built up in rocks that have been underground for eons can cause them to shatter. Exfoliation also occurs when the outer surfaces of rocks split off in flat flakes. This is believed to be caused by the stresses put on the rock by repeated thermal expansions and contractions, which induces fracturing parallel to the original surface. Chemical weathering processes probably play a more important role in deserts than was previously thought. The necessary moisture may be present in the form of dew or mist. Groundwater may be drawn to the surface by evaporation, and the formation of salt crystals may dislodge rock particles as sand or disintegrate rocks by exfoliation. Shallow caves are sometimes formed at the base of cliffs by this means. As the desert mountains decay, large areas of shattered rock and rubble occur. The process continues and the end products are either dust or sand. Dust is formed from solidified clay or volcanic deposits, whereas sand results from the fragmentation of harder granites, limestone and sandstone. There is a certain critical size, about 0.5 millimeters, below which further temperature-induced weathering of rocks does not occur, and this provides a minimum size for sand grains. As the mountains are eroded, more and more sand is created. At high wind speeds, sand grains are picked up off the surface and blown along, a process known as saltation. The whirling airborne grains act as a sand blasting mechanism which grinds away solid objects in its path as the kinetic energy of the wind is transferred to the ground. The sand eventually ends up deposited in level areas known as sand fields or sand seas, or piled up in dunes. Features. Many people think of deserts as consisting of extensive areas of billowing sand dunes because that is the way they are often depicted on TV and in films, but deserts do not always look like this. Across the world, around 20% of desert is sand, varying from only 2% in North America to 30% in Australia and over 45% in Central Asia. Where sand does occur, it is usually in large quantities in the form of sand sheets or extensive areas of dunes. A sand sheet is a near-level, firm expanse of partially consolidated particles in a layer that varies from a few centimeters to a few meters thick. The structure of the sheet consists of thin horizontal layers of coarse silt and very fine to medium grain sand, separated by layers of coarse sand and pea gravel which are a single grain thick. These larger particles anchor the other particles in place and may also be packed together on the surface so as to form a miniature desert pavement. Small ripples form on the sand sheet when the wind exceeds 24 km per hour, 15 miles per hour. They form perpendicular to the wind direction and gradually move across the surface as the wind continues to blow. The distance between their crests corresponds to the average length of jumps made by particles during saltation. The ripples are ephemeral and a change in wind direction causes them to reorganize. Diagram showing bark and dune formation, with the wind blowing from the left. Sand dunes are accumulations of wind-blown sand piled up in mounds or ridges. They form downwind of copious sources of dry, loose sand and occur when topographic and climatic conditions cause airborne particles to settle. As the wind blows, saltation and creep take place on the windward side of the dune and individual grains of sand move uphill. When they reach the crest, they cascade down the far side. The upwind slope typically has a gradient of 10 degrees to 20 degrees while the lee slope is around 32 degrees. the angle at which loose dry sand will slip. As this wind-induced movement of sand grains takes place, the dune moves slowly across the surface of the ground. Dunes are sometimes solitary, but they are more often grouped together in dune fields. When these are extensive, they are known as sand seas or ergs. The shape of the dune depends on the characteristics of the prevailing wind. Barken dunes are produced by strong winds blowing across a level surface and are crescent-shaped with the concave side away from the wind. When there are two directions from which winds regularly blow, a series of long, linear dunes known as scythe dunes may form. These also occur parallel to a strong wind that blows in one general direction. Transverse dunes run at a right angle to the prevailing wind direction. Star dunes are formed by variable winds, and have several ridges and slip faces radiating from a central point. They tend to grow vertically. They can reach a height of 500 m, 1,600 feet, making them the tallest type of dune. Rounded mounds of sand without a slip face are the rare dome dunes, found on the upwind edges of sand seas. In deserts where large amounts of limestone mountains surround a closed basin, such as at White Sands National Park in south-central New Mexico, occasional storm runoff transports dissolved limestone and gypsum into a low-lying pan within the basin where the water evaporates, depositing the gypsum and forming crystals known as solnite. The crystals left behind by this process are eroded by the wind and deposited as vast white dune fields that resemble snow-covered landscapes. These types of dune are rare, and only form in closed arid basins that retain the highly soluble gypsum that would otherwise be washed into the sea. A large part of the surface area of the world's deserts consists of flat, stone-covered plains dominated by wind erosion. In Ulian deflation, the wind continually removes fine-grained material, which becomes wind-blown sand. This exposes coarser-grained material, mainly pebbles with some larger stones or cobbles, leaving a desert pavement, an area of land overlaid by closely packed smooth stones forming a tessellated mosaic. Different theories exist as to how exactly the pavement is formed. It may be that after the sand and dust is blown away by the wind the stones jiggle themselves into place. Alternatively, stones previously below ground may in some way work themselves to the surface. Very little further erosion takes place after the formation of a pavement, and the ground becomes stable. Evaporation brings moisture to the surface by capillary action and calcium salts may be precipitated, binding particles together to form a desert conglomerate. In time, bacteria that live on the surface of the stones accumulate a film of minerals and clay particles, forming a shiny brown coating known as desert varnish. Other non-sandy deserts consist of exposed outcrops of bedrock, dry soils or aridisols, and a variety of landforms affected by flowing water, such as alluvial fans, sinks or playas, temporary or permanent lakes, and oases. A hamada is a type of desert landscape consisting of a high rocky plateau where the sand has been removed by aeolian processes. Other landforms include plains largely covered by gravels and angular boulders, from which the finer particles have been stripped by the wind. These are called Reg in the Western Sahara, Sur in the Eastern Sahara, Gibber Plains in Australia and Sai in Central Asia. The Tassili Plateau in Algeria is a jumble of eroded sandstone outcrops, canyons, blocks, pinnacles, fissures, slabs and ravines. In some places the wind has carved holes or arches, and in others, it has created mushroom-like pillars narrower at the base than the top. On the Colorado Plateau, it is water that has been the prevailing eroding force. Here, rivers, such as the Colorado, have cut their way over the millennia through the high desert floor, creating canyons that are over a mile, 6,000 feet or 1,800 meters, deep in places, exposing strata that are over 2 billion years old. Dust storms and sandstorms. Main article, dust storm. Sand and dust storms are natural events that occur in arid regions where the land is not protected by a covering of vegetation. Dust storms usually start in desert margins rather than the deserts themselves, where the finer materials have already been blown away. As a steady wind begins to blow, fine particles lying on the exposed ground begin to vibrate. At greater wind speeds, some particles are lifted into the airstream. When they land, they strike other particles which may be jerked into the air in their turn, starting a chain reaction. Once ejected, these particles move in one of three possible ways, depending on their size, shape and density: suspension, saltation or creep. Suspension is only possible for particles less than 0.1 millimeters, 0.0039 in diameter. In a dust storm, these fine particles are lifted up and wafted aloft to heights of up to 6 kilometers, 3.7 mi. They reduce visibility and can remain in the atmosphere for days on end, conveyed by the trade winds for distances of up to 6,000 kilometers, 3,700 mi. Denser clouds of dust can be formed in stronger winds, moving across the land with a billowing leading edge. The sunlight can be obliterated and it may become as dark as night at ground level. In a study of a dust storm in China in 2001, it was estimated that 6.5 million tons of dust were involved, covering an area of 134 million kilometers, 52 million square mi. The mean particle size was 1.44 micrometer. A much smaller scale, short-lived phenomenon can occur in calm conditions when hot air near the ground rises quickly through a small pocket of cooler, low-pressure air above, forming a whirling column of particles, a dust devil. Wind-blown particles, 1 creep 2. Saltation 3. Suspension 4. Wind current. Sandstorms occur with much less frequency than dust storms. They are often preceded by severe dust storms and occur when the wind velocity increases to a point where it can lift heavier particles. These grains of sand, up to about 0.5 millimeters, 0.020 in diameter, are jerked into the air but soon fall back to Earth, ejecting other particles in the process. Their weight prevents them from being airborne for long and most only travel a distance of a few meters, yards. The sand streams along above the surface of the ground like a fluid, often rising to heights of about 30 centimeters, 12 in. In a really severe steady blow, 2 m, 6 feet 7 in, is about as high as the sand stream can rise, as the largest sand grains do not become airborne at all. They are transported by creep, being rolled along the desert floor or performing short jumps. During a sandstorm, the wind-blown sand particles become electrically charged. Such electric fields, which range in size up to 80 kV/m, can produce sparks and cause interference with telecommunications equipment. They are also unpleasant for humans and can cause headaches and nausea. The electric fields are caused by the collision between airborne particles and by the impacts of saltating sand grains landing on the ground. The mechanism is little understood, but the particles usually have a negative charge when their diameter is under 250 micrometers and a positive one when they are over 500 micrometers. Ecology and biogeography. Deserts and semi-deserts are home to ecosystems with low or very low biomass and primary productivity in arid or semi-arid climates. They are mostly found in subtropical high-pressure belts and major continental rain shadows. Primary productivity depends on low densities of small photoautotrophs that sustain a sparse trophic network. Plant growth is limited by rainfall, temperature extremes and desiccating winds. Deserts have strong temporal variability in the availability of resources due to the total amount of annual rainfall and the size of individual rainfall events. Resources are often ephemeral or episodic, and this triggers sporadic animal movements and pulse and reserve or boom-bust ecosystem dynamics. Erosion and sedimentation are high due to the sparse vegetation cover and the activities of large mammals and people. Plants and animals in deserts are mostly adapted to extreme and prolonged water deficits, but their reproductive phenology often responds to short episodes of surplus. Competitive interactions are weak. Flora. Xerophytes, cardan cacti in the Baja California desert, Catavina region, Mexico. Plants face severe challenges in arid environments. Problems they need to solve include how to obtain enough water, how to avoid being eaten and how to reproduce. Photosynthesis is the key to plant growth. It can only take place during the day as energy from the sun is required, but during the day, many deserts become very hot. Opening stomata to allow in the carbon dioxide necessary for the process causes evapotranspiration, and conservation of water is a top priority for desert vegetation. Some plants have resolved this problem by adopting crassulacean acid metabolism, allowing them to open their stomata during the night to allow CO2 to enter, and close them during the day, or by using C4 carbon fixation. Many desert plants have reduced the size of their leaves or abandoned them altogether. Cacti are present in both North and South America with a post-Gondwana origin. The genus is desert specialist, and in most species, the leaves have been dispensed with and the chlorophyll displaced into the trunks, the cellular structure of which has been modified to allow them to store water. When rain falls, the water is rapidly absorbed by the shallow roots and retained to allow them to survive until the next downpour, which may be months or years away. The giant saguaro cacti of the Sonoran Desert form forests, providing shade for other plants and nesting places for desert birds. Saguaro grows slowly but may live for up to 200 years. The surface of the trunk is folded like a concertina, allowing it to expand, and a large specimen can hold 8 tons of water after a good downpour. Other xerophytic plants have developed similar strategies by a process known as convergent evolution. They limit water loss by reducing the size and number of stomata, by having waxy coatings and hairy or tiny leaves. Some are deciduous, shedding their leaves in the driest season, and others curl their leaves up to reduce transpiration. Others, such as aloes, store water in succulent leaves or stems or in fleshy tubers. Desert plants maximize water uptake by having shallow roots that spread widely, or by developing long taproots that reach down to deep rock strata for groundwater. The saltbush in Australia has succulent leaves and secretes salt crystals, enabling it to live in saline areas. In common with cacti, many have developed spines to ward off browsing animals. Some desert plants produce seed which lies dormant in the soil until sparked into growth by rainfall. With annuals, such plants grow with great rapidity and may flower and set seed within weeks, aiming to complete their development before the last vestige of water dries up. For perennial plants, reproduction is more likely to be successful if the seed germinates in a shaded position, but not so close to the parent plant as to be in competition with it. Some seed will not germinate until it has been blown about on the desert floor to sclarify the seed coat. The seed of the mesquite tree, which grows in deserts in the Americas, is hard and fails to sprout even when planted carefully. When it has passed through the gut of a pronghorn it germinates readily, and the little pile of moist dung provides an excellent start to life well away from the parent tree. The stems and leaves of some plants lower the surface velocity of sand-carrying winds and protect the ground from erosion. Even small fungi and microscopic plant organisms found on the soil surface, so-called cryptobiotic soil, can be a vital link in preventing erosion and providing support for other living organisms. Cold deserts often have high concentrations of salt in the soil. Grasses and low shrubs are the dominant vegetation here, and the ground may be covered with lichens. Most shrubs have spiny leaves and shed them in the coldest part of the year. Fauna. Main article, xerocole. Animals adapted to live in deserts are called xerocoles. There is no evidence that body temperature of mammals and birds is adaptive to the different climates, either of great heat or cold. In fact, with a very few exceptions, their basal metabolic rate is determined by body size, irrespective of the climate in which they live. Many desert animals, and plants, show especially clear evolutionary adaptations for water conservation or heat tolerance, and so are often studied in comparative physiology, ecophysiology, and evolutionary physiology. One well-studied example is the specializations of mammalian kidneys shown by desert-inhabiting species. Many examples of convergent evolution have been identified in desert organisms, including between cacti and euphorbia, kangaroo rats and gerbils, Phrynosoma and moloch lizards. Deserts present a very challenging environment for animals. Not only do they require food and water, but they also need to keep their body temperature at a tolerable level. In many ways, birds are the ablest to do this of the higher animals. They can move to areas of greater food availability as the desert blooms after local rainfall and can fly to faraway water holes. In hot deserts, gliding birds can remove themselves from the overheated desert floor by using thermals to soar in the cooler air at great heights. In order to conserve energy, other desert birds run rather than fly. The cream-colored courser flits gracefully across the ground on its long legs, stopping periodically to snatch up insects. Like other desert birds, it is well camouflaged by its coloring and can merge into the landscape when stationary. The sun grouse is an expert at this and nests on the open desert floor dozens of kilometers, miles, away from the water hole it needs to visit daily. Some small diurnal birds are found in very restricted localities where their plumage matches the color of the underlying surface. The desert lark takes frequent dust baths, which ensures that it matches its environment. Water and carbon dioxide are metabolic end products of oxidation of fats, proteins, and carbohydrates. Oxidizing a gram of carbohydrate produces 0.60 grams of water, a gram of protein produces 0.41 grams of water, and a gram of fat produces 1.07 grams of water, making it possible for xerocoles to live with little or no access to drinking water. The kangaroo rat, for example, makes use of this water of metabolism and conserves water both by having a low basal metabolic rate and by remaining underground during the heat of the day, reducing loss of water through its skin and respiratory system when at rest. Herbivorous mammals obtain moisture from the plants they eat. Species such as the Adax antelope, dik-dik, Grant's gazelle and oryx are so efficient at doing this that they apparently never need to drink. The camel is a superb example of a mammal adapted to desert life. It minimizes its water loss by producing concentrated urine and dry dung, and is able to lose 40% of its body weight through water loss without dying of dehydration. Carnivores can obtain much of their water needs from the body fluids of their prey. Many other hot desert animals are nocturnal, seeking out shade during the day or dwelling underground in burrows. At depths of more than 50 centimeters, 20 in, these remain at between 30 and 32 degrees Celsius, 86 and 90 degrees Fahrenheit, regardless of the external temperature. gerbils, desert rats, kangaroo rats and other small rodents emerge from their burrows at night, and so do the foxes, coyotes, jackals and snakes that prey on them. Kangaroos keep cool by increasing their respiration rate, panting, sweating and moistening the skin of their forelegs with saliva. Mammals living in cold deserts have developed greater insulation through warmer body fur and insulating layers of fat beneath the skin. The Arctic weasel has a metabolic rate that is 2 or 3 times as high as would be expected for an animal of its size. Birds have avoided the problem of losing heat through their feet by not attempting to maintain them at the same temperature as the rest of their bodies, a form of adaptive insulation. The emperor penguin has dense plumage, a downy underlayer, an air insulation layer next to the skin and various thermoregulatory strategies to maintain its body temperature in one of the harshest environments on Earth. The desert iguana, Dipsosaurus dorsalis, is well adapted to desert life. Being ectotherms, reptiles are unable to live in cold deserts but are well suited to hot ones. In the heat of the day in the Sahara, the temperature can rise to 50 degrees Celsius, 122 degrees Fahrenheit. Reptiles cannot survive at this temperature, and lizards will be prostrated by heat at 45 degrees Celsius, 113 degrees Fahrenheit. They have few adaptations to desert life and are unable to cool themselves by sweating, so they shelter during the heat of the day. In the first part of the night, as the ground radiates the heat absorbed during the day, they emerge and search for prey. Lizards and snakes are the most numerous in arid regions, and certain snakes have developed a novel method of locomotion that enables them to move sidewards and navigate high sand dunes. These include the horned viper of Africa and the sidewinder of North America, evolutionarily distinct but with similar behavioral patterns because of convergent evolution. Many desert reptiles are ambush predators and often bury themselves in the sand, waiting for prey to come within range. Amphibians might seem unlikely desert dwellers, because of their need to keep their skins moist and their dependence on water for reproductive purposes. In fact, the few species that are found in this habitat have made some remarkable adaptations. Most of them are fossorial, spending the hot dry months estivating in deep burrows. While there they shed their skins a number of times and retain the remnants around them as a waterproof cocoon to retain moisture. In the Sonoran Desert, couch spadefoot toad spends most of the year dormant in its burrow. Heavy rain is the trigger for emergence, and the first male to find a suitable pool calls to attract others. Eggs are laid and the tadpoles grow rapidly as they must reach metamorphosis before the water evaporates. As the desert dries out, the adult toads rebury themselves. The juveniles stay on the surface for a while, feeding and growing, but soon dig themselves burrows. Few make it to adulthood. The water-holding frog in Australia has a similar life cycle and may estivate for as long as 5 years if no rain falls. The desert rain frog of Namibia is nocturnal and survives because of the damp sea fogs that roll in from the Atlantic. Invertebrates, particularly arthropods, have successfully made their homes in the desert. Flies, beetles, ants, termites, locusts, millipedes, scorpions and spiders have hard cuticles which are impervious to water, and many of them lay their eggs underground and their young develop away from the temperature extremes at the surface. The Saharan silver ant, Cataglyphis bombycina, uses a heat shock protein in a novel way and forages in the open during brief forays in the heat of the day. The long-legged darkling beetle in Namibia stands on its front legs and raises its carapace to catch the morning mist as condensate, funneling the water into its mouth. Some arthropods make use of the ephemeral pools that form after rain and complete their life cycle in a matter of days. The desert shrimp does this, appearing miraculously in new formed puddles as the dormant eggs hatch. Others, such as brine shrimps, fairy shrimps and tadpole shrimps, are cryptobiotic and can lose up to 92% of their body weight, rehydrating as soon as it rains and their temporary pools reappear. Human relations. Humans have long made use of deserts as places to live, and more recently have started to exploit them for minerals and energy capture. Deserts play a significant role in human culture with an extensive literature. Deserts can only support a limited population of both humans and animals.